Welcome to this year's ABC UTC in-depth web training. I'm Mary Lou Rawls-Newman, Director of Technology Transfer at the ABC UTC, and will be moderating the web training today. I'll be assisted by Paul Lyles, former Georgia State Bridge Engineer, Rick Liptak, Chief Bridge Construction Engineer with the Michigan DOT, and Don Diggeman, State Bridge Engineer with the Georgia DOT, all members of the ABC UTC Advisory Committee who will be moderating the Q&A sessions. Ali Javid, Ph.D. student at Florida International University, will be assisting in the web room. We'll now begin Module 1, Non-Proprietary Open Source Mix Design. We're pleased to introduce our speaker, Royce Floyd, Associate Professor in the School of Civil Engineering and Environmental Science at the University of Oklahoma. Royce?
Good morning, and thank you all for joining our web training this morning. In this module, I'm going to be talking about non-proprietary mix design kind of in general, as well as the specifics of the mix design developed with the ABC UTC. I want to start by acknowledging my co-PI, Dr. Jeff Volz, who was very instrumental in this effort, and I couldn't have done it without him, as well as the graduate students and undergraduate students that were involved in this project. There we go. So just to give a little history on UHPC, early development of a UHPC type material began in the 1970s, looking at high strength mortars and optimized particle gradations to give very high strength matrices for the material. And then in the 1980s and early 1990s, there was examination of incorporating steel fibers and synthetic fibers to increase the ductility of that matrix. The first UHPC was commercially available in Europe in the 1990s and then became available in North America around the year 2000. And since that time, UHPC has spread worldwide, has had a lot of interest, a lot of events like this that have been held, and a lot of applications that have gone into the field. So as we begin talking about UHPC, we want to talk about kind of what we mean when we say UHPC. And there are a lot of definitions that are out there, being that we are the Accelerated Bridge Construction University Transportation Center. We often rely heavily on the FHWA definition, which includes a compressive strength greater than 18 KSI. Previously, that was 21.7 KSI. So a high compressive strength, and then a post-cracking flexural strength of at least 720 PSI. So having a high tension strength as well. The American Concrete Institute defines UHPC as having a minimum compressive strength of 22,000 PSI, a tensile ductility in the form of elastic, plastic, or strain hardening behavior under uniaxial tension. And there are many other definitions for UHPC that are out there. France and Canada include different classifications of UHPC based on its compressive strength, but we can kind of put as a general definition that we're looking at a material with a compressive strength of between 18 and 30,000 PSI, a post-cracking tensile strength in the range of 700 to 900 PSI, and a number of other superior properties such as high flowability, very low to negligible permeability, minimum freeze-thaw susceptibility, all leading to a very high durability, a high impact resistance, flexural toughness, and then those properties being achieved by fibers, either steel or otherwise. In looking at creating UHPC, there are some basic principles that have been around throughout the history of UHPC development. One of those being looking at an enhanced homogeneity of the material by eliminating the coarse aggregate, enhancing the density by optimizing the particle packing density of the constituent materials, and then enhancing the ductility by providing those fibers. Again, these are typically steel, and that's mostly what we're going to cover today, and usually are incorporated at a level of 2% or more by volume. If we look at some basic properties for UHPC generally, this is a table of properties for a widely studied UHPC taken from the literature, but you can see that the density of about 155 pounds per cubic foot is a little higher than conventional concrete. The compressive strength for this material was 24 KSI at 28 days. It has a higher modulus of elasticity because of the higher compressive strength of about 7,000 KSI. You can see the tension strength measured using various methods of higher than 1 KSI. And then the other properties including shrinkage, creep, low chloride ion permeability, and high freeze-thaw resistance, even with 600 cycles. So if we think about the constituent materials for UHPC, typically we're always going to have Portland cement included, silica fume, and fine quartz sand as our primary constituents. Because of the low water cement ratios that are used, we're going to need high range water reducers, or we'll refer to in this presentation as HRWR, to get the workability that we need. Other materials can be included, silica flour or other forms of ground silica to fill out some of the particle size distribution, potentially small coarse aggregate particles, and then supplementary cementitious materials of other types. Steel fibers can have different properties depending on the supplier and again the type of the fiber. Straight, crimped, hooked, or twisted fibers have been used for UHPC, usually in the range of 0.5 to 1 inches in length, 0.005 to 0.02 inches in diameter, and having a high strength greater than 300 KSI, to where typically the fiber fails by pullout rather than failing in tension. But the most commonly used fibers are probably the 1/2 inch straight fibers at about 2% by volume, which is what's shown here being placed into the mixer in the field. In terms of mixture proportioning, there's a low water to binder ratio of about 0.15 to 0.25. Attempts to reduce the void space within the mixture, and we'll talk more about how to do that later on. And then to incorporate steel fibers to improve that ductility, but also to consider the effects of adequate flowability and fiber suspension. So balancing the flow, but having a high enough viscosity that the fibers are suspended in the matrix. And again, that overall idea of creating a homogeneous matrix with properties on the microscopic level rather than having, more of the large aggregate particles that create an obvious composite material. All the cementitious materials in UHPC may not hydrate, which can lead to, those materials really acting like aggregate particles and filling out the spaces within the matrix. And most commonly, UHPC that's been used in the field has been proprietary prepackaged type mix designs. In terms of mixing UHPC, it does require a higher mixing energy requirement because the water content is very low. There's typically no coarse aggregate in the mix, so you need something to provide the shearing action. So a high shear mixture is often used, but a longer mixing time can be used in a more traditional concrete mixer. And here we show a couple of different mixers that we have used here in Oklahoma. So on the left and right are vertical axis pan mixers used on projects in the field. And the one in the middle is a horizontal shaft paddle mixer that we use in our lab. The mixing procedure consists of blending the dry components. So for a non-proprietary mix, that often means adding the different components separately, blending those all together. Then adding the water and the admixtures, allowing time for the mixture to achieve fluidity, which is shown here on the right. So going from powder over to a fluid mix, at which point the fibers are added to the mixture. The mixing energy input or the specific mixer is going to have an effect on the mixing time, but mixing times generally are in the range of 15 to 20 minutes, but can be longer than 20 minutes, especially when you're having to blend the dry constituents. With that being the case, heat production from long mixing times can be an issue that needs to be considered, which can include chilling the constituents beforehand or replacing some of the water with ice. Once the material is mixed, it does have a high fluidity, very similar to self-consolidating concrete. We measure that fluidity with a flow test shown here on the left. And it can be proportioned with other flow properties for high slopes or overlays, but most of the time for the applications where we use UHPC, we're looking for that high fluidity to get it into these small deck panel joints or other types of application. Because of that high fluidity, careful planning is needed in placing UHPC. We need to consider what consistency is needed for the specific application of the UHPC to proportion for that. For typical UHPC, the formwork needs to be watertight because that high fluid mix is going to find its way out of any leak in the formwork. And here on the right, we see the result of a formwork failure where most of the material that was being used for repair leaked out of the formwork onto the ground around the bridge. We also need adequate moisture preparation for any adjoining concrete to ensure proper bond between the UHPC and the adjacent concrete. We need a continuous placement to ensure proper fiber distribution, so placing the fresh UHPC into fresh UHPC. And then over vibration or overdosing with the high range water reducer can lead to fiber settlement within the mix and not getting the proper distribution within the finished product. And then consideration of placement methods are important to prevent fiber alignment or to get the fiber alignment that's desired. Curing of UHPC has had a lot of different work done in that area. It has a higher set time, up to 24 or 36 hours, depending on how much of the admixtures are used. With very high admixture dosages, that set time can be pushed out. Elevated temperatures, moisture, and pressure can improve properties over time if that's a possibility. If heat curing is going to be used, it's often going to be in the realm of 90 degrees Celsius, and then somewhere 12 to 24 to even as high as 36 hours. Heat curing can lead to no additional strength gain after that curing period, though, and it's often very difficult to do. So in the current state of UHPC, heat curing is not typically necessary and it's often not practical, and so most of the time it's not being used. It's just important to seal the UHPC and ensure that the moisture is able to stay inside. Testing of UHPC uses methods that are very similar for conventional concrete, but requires modification to account for the properties of UHPC. And most of the testing methods that are currently used are included in ASTM-C 1856, which has those modifications for the standard test methods used for concrete. The flow table testing that I mentioned utilizes ASTM-C 1437 with a few modifications. Specimens are made using the same methods we use for conventional concrete, except that we place in a single layer and don't need any external consolidation. Smaller specimens are typically used for UHPC, so for example 3x6 cylinders for compression, and then increased load rates are used just to reduce the length of the time of the test, and that have been shown to be effective through extensive research over time. So for example, 150 psi per second for compression rather than the standard 35 plus or minus 7. Test cylinders must be ground plane. No capping can be used due to the high strength of the UHPC, so that it meets the specification given in ASTM-C 39. Direct tension strength is an important consideration for UHPC due to its post-cracking ductility and its contribution to the overall behavior of the structure. And a number of different test methods have been used, but what's becoming the most common is the 2-inch square cross-section specimen that's examined extensively by the FHWA and that was recently approved as AASHTO standard T397. Other test methods are out there, but they're not yet standardized. There have been a lot of applications for UHPC, again, being that this center focuses on bridges. A lot of the work that's been done here has related to bridges. There are a lot of places where UHPC can be used for connections, joints between bulb tees, joints between full depth deck panels is very common. Full-scale girders have been done in a few places, including bulb tee and pie-shaped girders. There have been a number of pedestrian bridges that have been built with UHPC across the world. Rehabilitation and retrofit is a big potential application for UHPC where it's seen a lot more use recently. Piles and foundations and then seismic force resisting elements are all possible places where UHPC could be beneficial. In terms of the specific research that we're talking about in this presentation today, the original motivation actually came from a repair and retrofit standpoint. And in Oklahoma, we have a lot of bridge deck joints that have had some deterioration over time. And there are a couple of examples shown here, the one on the left specifically from Oklahoma. But the idea was to use UHPC to come in and replace the area around the joints to be able to replace the steel angles used for armoring. And we would have a high impact resistant material adjacent to the joint that could then be ground to eliminate these bumps at the joint. So as part of a project sponsored by the Oklahoma DOT, we did a implementation project looking at using UHPC for this type of application on the State Highway 3E bridge over the North Canadian River here in Oklahoma, where we replaced a section on either side of the joint using UHPC. And you can see here kind of the comparison between the UHPC material and the elastomeric nosing that have been used on the rest of that joint. And we've been able to monitor over time that it has performed very well compared to the previously used repair materials. In-joint or in-region deterioration, pre-stressed beams is also something we've seen a lot of in Oklahoma. And UHPC was seen as a potential option for repairing some of this in-region deterioration. Cracks in live load continuity connections is another issue where UHPC was considered to be an option for repair here in Oklahoma. And we've conducted research at Oklahoma on both of these applications that we don't have time to talk about today. UHPC has been used for other types of repairs in the literature, including for steel girder ends and concrete girder ends at other places across the country. So with kind of that background on UHPC history, basic properties, et cetera, and thinking about this idea of using UHPC as a repair and retrofit material, we get to the point of, why non-proprietary UHPC? And for some of these applications, so say in some of the joints, as well as some of the repair and retrofit applications, a compressive strength of 30,000 PSI may not be the most important thing. The most important thing may be, does it bond well to the conventional concrete? Does it bond well to the reinforcing steel? And is it going to be durable over time? And non-proprietary UHPC gives a lot more flexibility to tailor those properties to the needs, which can lower the material costs to potentially make it more accessible for small repair and retrofit projects, or to give the DOTs more flexibility. Like what Mary Lou said, the ABC UTC Advisory Board consists of individuals from many of the different state DOTs. ABC UTC polls those DOTs as to research needs, and one that came up by many of the state DOTs was more access to non-proprietary UHPC mix designs. And so out of that, this project with ABC UTC and all the partners came about to examine non-proprietary UHPC class materials for multiple applications. And then for us specifically at OU, we were also working with our state DOT here in Oklahoma. The objectives of our work was to develop a UHPC mix using materials local to Oklahoma, and then to modify that as the ABC UTC non-proprietary UHPC mix to consider the differences in materials from the locations where our different partners are located, and to provide guidance for use of UHPC developed in one region in another region of the country. Also to evaluate the performance of that mix design, the repeatability using the tests that were recommended by FHWA for UHPC characterization, and then finally to look at the effect of fiber content on the different material properties and structural behavior of this mix design. So I won't repeat what Mary Lou said about the structure of this project, but we did involve all of the different partners within the ABC UTC. And one interesting thing that we were able to do was to send our local materials, say to FIU, for them to send us their local materials, to do the same thing with Washington University and Nevada, Reno, so that we could examine repeatability within different labs as well as across different labs. So the material properties that were examined kind of at the different locations included flowability, compressive strength, and flexural tensile strength, but we also examined at OU modulus elasticity, splitting tensile strength, direct tension strength, shrinkage creep, set time, and then freeze thaw resistance and rapid chloride ion permeability as measures of durability. And I'll talk about some of these today, but not all of them. All right, so if we look at developing a non-proprietary UHPC mix, kind of the basic thing to look at is the materials that are available. And again, typically we're going to use Portland cement, fine sand, silica fume, high range water reducer, fibers, and water. And within Portland cement, there are variations in the performance for different types of cement. We specifically examined type 1 and type 3 here at OU. And then, some of the Portland cement can be replaced with other supplementary cementitious materials beyond silica fume. And again, that makes a difference in how those are going to react with the cement and the other materials available at a given location. For the fine sand, there are other possible materials that can be used in that category, including glass powder, ground quartz, silica flour, other finely ground silicate materials, or other types potentially of small aggregates. And looking at the combinations of those materials is very important to get that high density and homogeneous matrix. Water cementitious materials ratio is very important to get high strength. We often hear you need 0.21 to 0.28 to get full hydration of the cement, and you need that water to be able to migrate, so you really need even more than that to be able to get full hydration. We're talking a water cementitious materials ratio in the range of 0.18 to 0.25 when we're talking about UHPC, which leads to a possibility for water to not disperse evenly, which can lead to desiccation, and also requires very high dosages of high range water reducer, and like we've already said, results in not all the cement hydrating such that we have cement acting as aggregate particles. There are a number of different steel fiber types that are available that could be examined, straight, crimped, hooked, or twisted, usually 1/2 inch to 1 inch in length, 0.005 to 0.02 inches in diameter, and again, 2% by volume is the most common, but others can be used. And then whatever fibers that are chosen, it's very important to consider the competing effects of flowability and fiber suspension to ensure you have adequate flowability, but also adequate viscosity to suspend those fibers. So we've talked a little bit about optimizing the particle packing within the mix, but we want to minimize the void space and increase the density of the matrix to get that homogeneous behavior. And so we can look at the gradations of the individual mixture constituents and try to optimize the combinations to get the tightest particle packing. That can be done using discrete element models, particle packing models, or optimization curves. And so one thing to consider that we considered as our starting point is there are a lot of UHPC formulations that are out there. We're talking about one of them today as the ABC UTC mix, but there are a lot of mixes that have been developed. I'll give you some references to a number of them at the end of this presentation. But a sample UHPC formulation may have 2/3 of the cementitious materials be Portland cement, 1/6 be silica fume, 1/6 be fly ash, have a 1-to-1 aggregate to cementitious materials ratio, water cement ratio 0.23, and 21 ounces per 100 pounds of cement of high range water reducer. But it's very difficult to just take a mix design and to use it without doing any adjustment for specific materials, because different fly ashes, different slag cements may react differently with the cement that's available in a given place, and may not give the same performance that you saw in another region of the country. So it's very important to at least do trial batches to ensure that the materials are going to work well together as anticipated. So at OU, for developing the non-proprietary UHPC mix that we developed here, we looked at 9 separate series in our ODOT project to consider some of the different variables that we've discussed in the previous slides. And we started with a baseline mix design from previous UHPC research, so very similar to the mix that was shown on the previous page. But we found very quickly that with the materials we had, we were not able to replicate those results immediately. So we then moved on to looking at the optimal water content, cement content, and high range water reducer proportions to get the flowability properties that we were looking for. And then to look at introducing supplementary cementitious materials to replace some portion of the cement that was required to get the compressive strength that we needed. Kind of once we had that general idea of what materials that we we're going to use for our mix, we moved on to optimizing the particle packing for the specific materials we had available. And so we were able to obtain particle gradations for all of the materials that were utilized. So the type 1 cement slag, fly ash, available sands. We used a fine masonry sand that was oven dried. And we looked at optimizing those with the Anderson and Anderson particle packing model. We used the Elchem Emma software initially to look at optimization relative to that particle packing model. We also developed a spreadsheet to do that where we could see the numbers more easily. Looked at about 3,400 different possible combinations that resulted in about 150 actual mixes that we tested. We then looked at the benefits of different cement types, so whether or not type 3 could give us improvement, especially at early ages, and then looked in more depth at the aggregate cementitious materials ratio, specifically honed in on using slag cement in UHPC. And then by that point, some additional research had come out. So we examined some mixed designs that had been recently developed. And then finally in Series J, which was our last series of development, combined the most promising variables from the previous series, added fibers to those, and looked at heat curing and its effects on this non-proprietary mix. So this shows the different mixes that were used to evaluate fiber addition and heat curing from that last series, Series J. So we have them labeled as UHPC 1, UHPC 2, and UHPC 3, which also have their corresponding Series J number. We chose the most promising mixes from that series that included, one included fly ash, one included type 3 cement, 2 of them included slag cement, and then all of them utilized 10% silica fume and had a 1-to-1 aggregate to cementitious materials ratio and a 0.2 water cementitious materials ratio. UHPC 2, or what was J3 in Series J, was the most promising mix design. According for compression, modulus of rupture, or flexural strength, and the cost of the materials. And if we look at the different heat curing regimens that were used, 36 hours of heat curing gave us the highest strengths. We had about 20 KSI for that J3 or UHPC 2 mix, so this guy. But in general, we were able to make above 18,000 PSI using the different heat curing regimens, or if we used no heat curing and took it out to 28 days, we were in that range of 18 to 20,000 PSI. In terms of flexural strength, most mixes were around the 2,000 PSI range for the ultimate stress, so including the fibers, so the gray bar shown here. The first cracking strength, which is basically the matrix strength, was slightly less than that, so we did see increased load carrying capacity after cracking. And for our unreinforced specimens, we did see some of these curved failure surfaces, which indicated some energy absorption just from the matrix after cracking. So based on that initial testing, we came to the mix design that is included in our ABC UTC project, or the ABC UTC non-proprietary mix design, which includes as a proportion of the total dry materials, 30% cement, 5% silica fume, 15% slag cement. Or if you look at that in terms of percent of cementitious, it's 60% cement, 10% silica fume, 30% slag cement, a 1-to-1 sand to aggregate ratio, again using oven dried masonry sand, water cement ratio 0.2. In terms of material properties for this mix, we looked at compressive strengths using our raw materials here in Oklahoma, as well as those shipped from FIU. We saw very similar performance between the two sets of materials. And then as we looked at different fiber percentages, we saw an increasing flexural strength as we increased the percentage of fibers across the board. We also examined bond with conventional concrete. So say if this was going to be used in a joint, examining how well our material bonded to that conventional concrete for different surface preparations. The white bar here shows the conventional concrete flexural strength. So for an inclined interface between the two, we had basically the same strength at the bonded interface as we had for the conventional concrete, or a higher strength at the interface than we had in the conventional concrete. For our vertical surface, we didn't see as high a performance, and then we had some issues with our exposed aggregate surface that ended up showing lower results due to a poor surface preparation. We also tested some conventional slab concrete panels connected with a UHPC joint using this non-proprietary mix. So here you can see the completed panels on the right, the form mark on the left. We tested these both statically and cyclically. And if we look at the results of these two, the non-proprietary mix had a very similar performance to the proprietary UHPC with a lower earlier age stiffness due to a lower modulus of the material, as well as a potential earlier cracking at the interface. And then in both cases, we exceeded the estimated capacity of a monolithic slab, and we experienced yielding of the reinforcing steel. In terms of examining durability for the non-proprietary mix, all of our freeze-thaw results had a relative dynamic modulus greater than 100, and then we had very low rapid chloride ion permeability at 28 days, out to negligible at 56 days. We also examined composite specimens with freeze-thaw and saw that even when we had failure of the specimens, the failure was initiated in the conventional concrete, but not at the interface between the UHPC and the conventional concrete when we used an exposed aggregate surface. All right, so that's kind of a few results from the mix that we had. David's going to talk more in depth about that. We're getting close to time on this presentation, so I'm going to go through the next few slides quickly, but really these are just to provide you an idea of what's going on in other parts of the country and to provide some references you can take a look at. But several states have examined non-proprietary UHPC, including Arizona, which looked at some of the same methods that we did to consider materials locally available at Arizona. They found compressive strengths in excess of 22 KSI and had a mix somewhere in the neighborhood of $400 to $1,000 per cubic yard. Michigan has done an extensive amount of work in this area, primarily at the University of Michigan. There are several references listed here you can take a look at if you would like. They did field applications with a 21.5 KSI compressive strength, a Michigan contractor performing the work, and had a mix that also included Portland cement and slag cement. And then in some of their published works, they estimated costs of non-proprietary UHPC in the $560 to about $850 per cubic yard. A study sponsored by Montana DOT looked at materials available in Montana, found up to a 20 KSI compressive strength, good material properties and durability, and then had an estimated cost of $300 to $350 per cubic yard without fibers, which if you added fibers would probably about double that amount. The University of Arkansas has done some good work in this area as well, finding a 22.5 KSI compressive strength at 90 days. They included fly ash, hence measuring the strength later on in the age. And they've also done some work including some larger aggregate sizes. The University of Nebraska did some work for the Nebraska DOT, again found a mix in the 17 to 20 KSI range in compressive strength, had an estimated cost of about $680 per cubic yard. PCI recently published some guidelines on using UHPC and also has published information on developing UHPC mixes with precasters that resulted in compressive strength of 16 to 24 KSI, had demonstrations of full-scale mixing and casting, and utilized several different mixers. So in conclusion, non-proprietary UHPC can achieve the superior properties needed for many applications, similar properties to commercial UHPC. The ABC UTC non-proprietary mix is estimated $400 to $800 per cubic yard, depending on the fiber content, and was shown in near full-scale joints to have yielding of the steel with a 5-inch lap length to provide adequate development length, provided a slab joint that had capacity exceeding what was expected for a monolithic slab, had excellent freeze-thaw performance, and had results in line with several other states and groups who have done work in similar areas. So with that said, if you look at the slides in the handouts, there are a number of other references that are very helpful to you as you're considering, potentially using non-proprietary UHPC. And I'd like to say thanks to all those who have sponsored this work.
Okay, thank you very much, Royce. I'd like to now turn it over to Paul Lyles, who will be moderating the Q&A session, assisted as needed by Rick Liptak for the first 3 modules. Paul?
Okay, Mary Lou, thank you. And Royce, real good. We're just about out of time. I'm only going to be able to ask a couple of questions, and so we'll get in. This one came in beforehand. And what are the prospects of using larger graded sand particles in your UHPC mixes in order to reduce costs?
So that's a good question, and we haven't done much with that here specifically. So my experience is limited. I would point you to looking at the work from the University of Arkansas, where they have done some mixes with those larger particles. Important things to consider are the quality of those aggregates, and then considering what is the target properties that you're looking for. And if your compressive strength target is a little bit lower, it may be very possible to do that.
Okay. Does a non-proprietary mix design need to be modified for locally found materials?
Potentially. So one of the things that we found specifically is that the materials available in different locations do behave a little differently, especially related to flowability and or we'll say high range water reducer demand. So it's very important to at least do some trial batches with the locally available materials to ensure that you're going to get the performance that you're anticipating.
Okay, it's 11:40 and we need to go on to our next module. All these questions hopefully will have answers and they will be posted later. We do have a number of other questions. So go ahead, Mary Lou.
Okay, thank you, Paul. We're at the end of the first 40-minute module. Thanks again to Royce for presenting Module 1.